Hi everyone, thank you very much for joining. My name is Roei, and this talk is titled When Arthur Has Neither Random Coins Nor Time to Spare, Superfast Derandomization of Proof Systems. And it's a joint work with Lijie Chen. My plan for this talk is to start by describing the background on the main topic that we are interested in, derandomization of proof systems, then talk about super fast, worst case derandomization of proof systems, and then in the main part of the talk, I'm going to talk about free lunch derandomization of proof systems into NP-type arguments. And in this part, I'm going to define a new computational model of computationally sound NP and talk about implications of this result in cryptography and in algorithms. And as you may have already noticed, this talk sits at the intersection of several topics. It's a talk about derandomization, it's a talk about interactive proofs, it's a talk about cryptography, and it has implications to solving sharp-set, so to algorithms. Let's begin with the background. So we're concerned with proof systems, where a verifier who is weak and a prover who is stronger interact on a common input X. And formally, a language L is in IP interactive proofs if there exists a probabilistic polynomial time verifier and an unbounded honest prover, such that on correct claims, when the verifier and prover interact, the verifier accepts, and on incorrect claim, no matter who the verifier is interacting with, it rejects with probability at least half. So it's information theoretic soundness. And of course, if the verifier is unhappy with the error probability of half, it can repeat the interaction to decrease it exponentially. And for simplicity, throughout the talk, we only care about public coin proof systems. So in each round, the verifier just tosses coins and sends them as plain text to the prover, and about perfect completeness. So on correct claims, the probability that the verifier accepts when interacting with the honest prover is 1. And we care about derandomization of interactive proofs. And of course, an easy observation is that we can't hope to derandomize general interactive proofs in polynomial time unless NP equals P space. This is because we can decide all of P space with interactive proofs. But on the other hand, when we derandomize an interactive proofs, it collapses into NP, because there's no reason for interaction anymore. If the verifier is completely predictable, the prover can conduct the interaction on its side and send it in one shot to the verifier. So we need to focus on subclasses of proof systems. And in this talk, we're going to focus on the subclass of proof systems with constantly many rounds. So when we take general interactive proofs and we restrict them to be of constantly many rounds, we get what is known as Arthur-Merlin protocols. So a language is in AM times C. C is the number of messages here, and it's a constant, and T is the running time. If there is a proof system with a T-time verifier, such that there are overall C messages involved in the proof system. So the verifier speaks first, the prover answers, and so on and so forth, and that most C messages have been exchanged, and C is a constant. And Baba and Moran show that you can simulate AM with C rounds with AM with just 2 rounds with a polynomial overhead. So it follows that AM is contained in the second level of the polynomial time hierarchy, pi 2. Or in other words, it seems to be much weaker than general proof systems. And it's widely conjectured that AM actually equals NP. So it's even weaker than that. It's not in the second level of the polynomial time hierarchy, it's just NP. And I particularly like this question because this is a question simultaneously about derandomization. Can we take the coins of a verifier in a proof system and simulate the verifier without coins? And it's also a question about the power of proof systems. Are constantly many rounds actually redundant, and can we simulate them with just an NP-type verifier? And I want to state what is known classical results about this conjecture, and to state them, I'm going to state them in a way that's not written in the original results, but that follows pretty much immediately for them. So let's define a constructive and useful property of truth tables. So fix pi as a property, just a set of truth tables. And we say that it's constructive in a class C if there is a C algorithm that gets the 2 to the n bit description of the truth table. So big N is 2 to the little n, and the truth table is over n bits, and decides whether or not the truth table has the property, is f in pi. Okay, and it's usually, say, something like a polynomial time algorithm. So it runs in time polynomial in big N, in the size of the truth table. And we say that the property is useful against some class D if every procedure in D fails to compute functions that have this property. So now we think of f as describing a function, and we say that this function is hard for procedures in D. And a classical result asserts that if there is a constructive property, where constructiveness here is in non-deterministic polynomial time, the polynomial is in the length of the truth table, that's useful against non-deterministic exponential size circuits, then AM equals NP. The conjecture is true. Okay, so it's a kind of circuit lower bound in the hypothesis, right? It's a property of truth tables that on the one hand is hard for circuits that are non-deterministic and have exponential size, and on the other hand, there is a uniform upper bound on at least recognizing truth tables with this property. You can recognize them in time that's polynomial in the length of the truth table. And notice that there is a slackness both in the hypothesis and in the conclusion here, because we assume that the upper bound is an arbitrary polynomial in the hypothesis, and we deduce that AM equals NP. But we don't know exactly how much of a polynomial overhead there is when simulating AM in N. And the main question driving the current work is superfast and free-lunch derandomization, which was first introduced in a work by Doron, Moshkovitz, and Zuckerman with a follow-up by the current authors. It asks, okay, classical results tell us that we can simulate under assumptions probabilistic time t in deterministic time t to the c, where c is a constant. But is C 1,000, a million, 3, 5? What is this constant C? Can we control it, get it to be as small as possible? And in particular, a dream result would be where C equals 1. Can we get the randomization with no overhead at all? Just simulate probabilistic time t in deterministic time t. And there are many recent no results for the BPP versus P setting, simulating algorithms. And the current work asks this question, superfast and free-lunch derandomization, in the context of proof systems, AM equals NP. Our first main result does precisely that. So informally, under assumptions, we can simulate Arthur-Merlin protocols with C messages and running time T by an NP verifier that runs in time N, that's the input length, times T to the C over 2, plus epsilon that's as small as you want. So for example, if we had an Arthur-Merlin protocol with 10 messages, so 5 rounds, and we get a time overhead in the simulation of n times t to the 5. And if there were 1,000 messages, 500 rounds, then we get an NP verifier running in time n times t to the 500. You might wonder why I call this a super fast randomization, because it seems to be really slow, t to the 500. The reason is that under assumptions, this is optimal. You can't do better. So let me be a bit more formal. So the assumptions that we're going to need for the upper bound are generalizations of the classical assumptions. Recall that the classical ones were like an n time n to the O of 1 constructive property useful against non-deterministic circuits of exponential size. Here we're going to need the following two assumptions, which refer to a tighter gap between the upper bound from the constructiveness and the lower bound from the usefulness. So in the first hypothesis, the constructiveness is in near linear time in the size of the truth table, and the usefulness is against procedures that are stronger than non-deterministic circuits. These are MAM circuits. So you can think of these as interactive procedures receiving near maximal advice that have 3 messages exchanged. And if you just think of little n to compare the time bound in the upper bound and the lower bound, the upper bound is slightly larger than 2 to the little n, and the lower bound is slightly lower than 2 to the little n. The second hypothesis is a straightforward generalization of the classical one. So we assume that for every integer k, there is a constructive property where constructiveness is in time slightly more than 2 to the k times little n, that's useful against non-deterministic procedures running in time slightly less than 2 to the kn and receiving near maximal advice. Under these two assumptions, for every polynomial t, we can get a derandomization that's super fast in the sense that I just said. The time overhead is n times t to the c over 2 plus epsilon. The complementary part of this result follows from previous work. It asserts that if sharp n s e t h is true, then the derandomization that we just saw is optimal. Where sharp n s e t h is the assumption that for every epsilon there is a k, such that non-deterministically solving sharp-SAT for KCNF formulas takes time more than 2 to the 1 minus epsilon n. It's a strong member of the exponential time hypothesis family that asserts hardness for non-deterministic machines, but hardness for the counting problem, or sharp set. It follows from a work of Williams that uses the Sanchak protocol. Okay, that's the first main result. We maybe under assumptions nailed the optimal overhead. What can we do now? Can we do better than that? So the main part of the talk and of this work discusses a free lunch derandomization that somehow bypasses this barrier. The idea is to avoid the overhead of t to the c over 2 end of n by allowing error in the derandomization, not insisting on worst case error, on worst case derandomization, but insisting that this error will be undetectable. So bad inputs and bad proofs for the derandomization might exist, but they're infeasible to find. So let's just the cleanest setting to present this result is that of doubly efficient proof systems. So it would be derandomization of doubly efficient proof systems. So let me just define doubly efficient proof systems. These are just like the general proof systems, except that we insist on the prover being efficient. So we still have a prover that is stronger than the verifier, because the verifier runs in time t, and the honest prover runs in time polynomial in t. Completeness and soundness are exactly the same. When the verifier and honest prover interact on a correct claim, the verifier accepts. And on an incorrect claim, we have an information theoretic soundness. No matter which strategy the adversarial prover implements, the verifier rejects with high probability. And the result that we will see is de-randomizing this class of proof systems, doubly efficient proof systems with constantly many rounds, into NP-type verifiers with only computational soundness, the sense that it's infeasible to find inputs and proofs that fool it. And let's define this notion, which is actually a very natural notion. If I would have told you that it was defined in the 80s, you would have believed me. Let's call it computationally sound NP. In the paper, we use a different notation, but this notation seems to be nicer. So we say that the problem is in computationally sound n time t, if there's a deterministic verifier, it's an NP-type verifier that runs in time t, and an honest prover that runs in time polynomial in t, that satisfy the following two conditions. So completeness is just what you expect. On correct claims, when the prover and the verifier look at the same claim, the prover sends a proof to the verifier and the verifier accepts. There's no probability here, right? Because the verifier is just an NP-type verifier. It receives a proof. And soundness now holds not information theoretically, but with respect to computationally bounded adversaries. So for every poly t-time machine, P prime, where the polynomial may be arbitrarily large, but this is a bounded, computationally efficient adversary, the probability that the adversary manages to find an input and a proof that fool the verifier is negligible. So this is the part where I just mentioned. The probability that P prime manages to find X and pi such that X is an incorrect claim, and nevertheless, when V sees X and the proof pi, it says yes, is negligible. So the soundness is computational, and it's on average, in the sense that it doesn't need to hold for all inputs, it only needs to hold for inputs that are feasible to find. And the main result is under a complexity theoretic hardness assumption that I will present next. For every constant C and polynomial T, we can de-randomize doubly efficient interactive proofs with C messages with no overhead and computational soundness of the NP-type verifier. So no matter how large C was, 1,000, 1,000,000, we're ending up with an NP-type verifier that uses essentially the same running time as the original interactive verifier, decides the same problem, and has computational soundness. And I promised to define the computationally sound NP model, which I did, and I promised two applications. So let me present the applications now. The first one is NP-type arguments for sharp set, or solving sharp set in computationally sound NP. So under a similar hardness assumption to the one that I just mentioned, in fact, a weaker one, for every epsilon, there is a deterministic verifier that gets an n-bit formula, polynomial size or even larger than that, runs in time 2 to the epsilon n, and satisfies the following two conditions. So there is an efficient prover that can send a proof to this verifier that will cause the verifier to print the precise number of satisfying assignments to this formula. So it's not an approximation, it's the precise number of satisfying assignments. And on the other hand, for every exponential time adversary, the probability that the adversary manages to find the formula and find the proof that will cause the verifier to output an incorrect count is negligible in 2 to the n. It's tiny. This is basically solving sharp-sat in time 2 to the epsilon n, where epsilon is as small as you want, using a proof and with computational soundness. The widely believed non-deterministic exponential time hypothesis asserts that you cannot do it with information theoretic soundness. And this result says that under a hardness assumption, you can do it when you relax the soundness to be computational. The second application that I want to talk about is to cryptography. And recall that in cryptography, the Fiat-Shamir heuristic is a way to remove interaction in interactive proofs, reduce it to just basically 2 messages. And jumping ahead, the derandomization algorithm that we will use is essentially a complexity theoretic variant of Fiat-Shamir. It's very close to that. So the corollary that applies to cryptography is that under a complexity theoretic hardness assumption, a variant of Fiat-Shamir works for the class of constant round doubly efficient proof systems. And in particular, usually in cryptography, Fiat-Shamir can be proven to work for certain classes of proof systems under crypto assumptions, such as LWE. But here, there is no assumption from crypto, no one-way functions, just a complexity theoretic hardness assumption. And what is this assumption? Let me now present it. The hardness assumption is cumbersome to state, but it's quite natural. We assume that there is a function mapping t bits to k bits, where k is much smaller, k is n to the little of 1, such that, on the one hand, the costs of computing each output bit of the function, each of the output bit of the k output bits, is t prime. T prime is t times k. So the cost of one output bit is t prime. And we want to say that the function is not batch computable. Like trivially, of course, you can print the k output bits in time t prime times k, just compute each individual one. But we want to say that you cannot magically do it in a cost that is close to the cost of printing just one output bit. So for every algorithm running in time t prime, the cost of one bit, times k to the power of 0.0001, and being aided by an oracle, it can send the t-length queries to a linear time interactive oracle. And for every polynomial time sampleable distribution over the inputs, with all but negligible probability over a sample of input from this distribution, the algorithm cannot print all the k bits without some noticeable corruption in this string, like 0.001 corruption when it tries to print. And I know that this is cumbersome, so let's parse it just a little bit, okay? At the base of it, this is what can be thought of as a mildly strong direct product hypothesis. Strong direct product hypothesis, in particular mildly strong direct product hypothesis, are quite believable and quite appealing. In particular, in our case, when we only assume that you can't batch compute the k bits in time, that is the time to compute 1 bit times k to the 0.001, they're very appealing. And our hypothesis has 2 strengthenings over such a baseline hypothesis. First is that hardness is over all polytime sampleable distributions. Usually in direct product hypothesis, the hardness is over the uniform distribution or over product distributions, but here we assume that hardness is over input sampleable from all polytime sampleable distributions, and that's the main strengthening of the hypothesis from a mildly strong direct product one. The second strengthening is that hardness holds even when the adversary is given an oracle, particularly an interactive, an oracle to every language, to every promise problem solvable in AM linear time with C turns. And this, I argue, is actually the less important strengthening, because if you work out the parameters, the oracle seems too weak to even compute just one output bit. And for this reason, even replacing this oracle to AM with an oracle to linear space still makes for a reasonable and appealing hardness assumption. Now, we are not completely done yet. This assumption suffices for the corollary of sharp-sat and more generally to de-randomize doubly efficient interactive proofs with constantly many rounds and a small number of random coins, t to the little of 1. To reduce the general case of constant round doubly efficient interactive proofs to the case of ones with few t to the little of 1 random coins, we need another hardness assumption, which is more similar to the ones that we saw in the superfast case. Okay, let's turn to the proof, just very quickly to see the main idea. So the natural thing fails using classical black box techniques in derandomization. So the natural classical thing to do would be to use a PRG at each turn to reduce the number of coins to be sublogarithmic, little o of log t. And then after we do that, instead of having the interaction, the prover can just send the tree of all possible interactions in one shot to the verifier. Since the seed is much less than log t, all possible interactions will be like t to the little o of 1, and thus it won't induce a serious time overhead, assuming that the PRG is fast and such a PRG exists and so on. And why does this fail? Well, who does the PRG need to fool? So let's assume that we're replacing the coins at the third round by pseudo-random coins. Instead of having the verifier sending random coins, it sends coins used by the produced by a PRG. The distinguisher that it needs to fool is the residual value of the game, the probability that the verifier accepts when interacting with the prover over correct claims and incorrect claims. Right? Since we care about perfect completeness, let's just focus on incorrect claims. But if we want the PRG to fool all residual values of the game that are produced when considering every possible transcript that happened so far, then it's going to need seed at least log t, provably. And if it's going to need seed at least log t in every round, we're going to get exactly the same overhead that we were trying to avoid, t to the c over 2. Similar, now, you can observe that actually we don't need to consider all t-bit transcripts, because the transcript up to the third round was produced by a conversation between an efficient prover and an efficient verifier, since we only care about efficient adversaries. But if we're trying to fool all transcript produced by poly t-time algorithms, provably we need a runtime of more than poly t. And again, we're stuck. We don't want to pay a runtime of poly t. We want to avoid paying at all. So what's going on? Why did this idea fail? Well, the source of trouble is that we tried to build a single PRG that works against all transcripts of length t, or alternatively, all efficient transcripts of length t, efficiently producible in time poly t. And the way to avoid this and solve the problem is to, instead of using a PRG, use a targeted PRG. This is a special type of PRG that gets a specific transcript as explicit input and fools the residual value of the game only for that particular transcript that happened up to that point. So in every round, instead of using random coins, we're going to use pseudo-random coins produced by a targeted PRG that gets the transcript up to that point as explicit input and only fools the distinguisher, the residual value of the game, when the distinguisher is given this particular transcript. And indeed, under assumptions, there exists such a PRG with seed length much smaller than log t, epsilon times log t, for an arbitrarily small epsilon. And indeed, people who are familiar with the Fiat-Shamir heuristic in cryptography can notice that this algorithmic method is very similar to the Fiat-Shamir heuristic. Derandomization just replaces a hash function, which was used in Fiat-Shamir, with a targeted PRG that we use right now in derandomization. So let me wrap up by mentioning the takeaways and some open questions. So the main results are a conditionally optimal worst-case derandomization of AM and a free lunch derandomization of doubly efficient interactive proofs into NP-type arguments, introducing a new model of computationally sound NP, solving under assumptions sharpsat in non-deterministic time 2 to the epsilon n, where epsilon is arbitrarily small, in this model of computational soundness NP verifiers, and showing a complexity variant of Fiat-Shamir that can be proven to work under complexity type assumptions. And there are many open problems and unexplored directions here. First, is the hardness assumption necessary, both for the worst case derandomization and for the free lunch derandomization? Can you either improve on the hardness assumption or show that it's necessary? In terms of crypto, can we analyze this complexity variant of Fiat-Shamir in more settings than just constant round doubly efficient proof systems? And in others, going beyond Fiat-Shamir, can we replace hash functions, in particular correlation intractable hash functions, with targeted PRGs in other settings? And in terms of algorithms, what can be done in this model of computationally sound NP other than just solving sharp set faster than we knew how to do? That's it. Thank you very much for your attention.